This is Module 13, Lesson 1. In this module, we're going to look at solutions. This is another module, kind of like Module 12, where part of it will be very concept-based, meaning you're going to have a lot of vocabulary words and things to memorize, but little to do. And then part of it will require you to do some more. There will be more equations and things like that, more math calculations that go with it. So make of that what you will. Know that I'm not going to read every slide to you when it comes down to just being a lot of vocabulary words. So first we have this. You need to make sure that you get the vocab down and the definitions. You can pause the video and then join me when you're ready for some discussion of it. So as you can see, you have the different vocab that goes with solutions right here. And then you have some review of solutions. This is review right here from Module 2. All of these things that we learned way back then, you may need to go back to review again so that you remember it. Something that I would like to add to just a little bit is this last statement down here. It's talking about dissolving and how substances that dissolve most readily in water are ionic and polar substances. We have this expression in chemistry that says like dissolves like. Whoops, that does not look like an L, does it? What that means, what like dissolves like means, is that similar things will dissolve each other. Well, what do I mean by similar? I mean things like polar. Polar things will dissolve other polar things. Non-polar things will dissolve other non-polar things. Ionic dissolves ionic, etc. Whenever you try to mix two things that aren't alike, they typically will not mix. A good example is oil and water. Oil is non-polar and water is polar. So when you try to put the two of them together, they won't dissolve. And a couple other words that go with that. If something won't dissolve, the word for that is immiscible. If they will dissolve, then you call them miscible. So oil and water are immiscible, which simply means they won't dissolve in each other. And then something like salt and water, they are miscible, meaning they will mix together. Okay, a little bit about solution process or solvation. One of the best examples that I can think of for this is a Tyler DeWitt video. So I'm going to put a link on the Canvas page for Tyler DeWitt's video about dissolving or the dissolving process. And I would like it if you could go back and you could watch that, because he shows you with a really good explanation, a really good visual, how the solvent surrounds the solute and breaks it up and pulls it out into solution. So he does a much better job than I can do with this little writing utensil here in a PowerPoint. So go back and look for that link on this. You can read the words that I have here, but if you would like to see it done, he has a really good video. Now, a word about electrolytes and non-electrolytes. Once again, pause, get this written down, and then come back for some conversation. Electrolytes are very important for us because your heart beats off of electricity, and your blood has electrolytes in it, which lets electricity flow. If it didn't, then your heart would not be able to basically beat, because electrical impulses wouldn't be able to be sent. Your muscles work off of electricity, so your muscles wouldn't work if you didn't have enough electrolytes inside of you. And this is how people end up getting really sick if they end up with a lot of vomiting or diarrhea, is they lose a lot of their electrolytes. So one of the things that they have them drink is either Gatorade or Pedialyte, because what it has in it is electrolytes. Now, if you have electrolytes, you can have strong or you can have weak ones. When it says over here that they're caused by dissociation into ions, we did this before back in Module 9 when we did net ionic equations, and we drew how this broke apart. Like in a net ionic equation, that this broke up into Na pluses and Cl minuses. Well, these are ions, so strong electrolytes break apart completely like this. And remember, if it had coefficients or subscripts like this, that those turn into coefficients, that this would dissociate into Mg plus 2 and 2 fluorines. And so basically, whenever it breaks up into a lot of pieces like this, That makes it a strong electrolyte. Those things conduct electricity really well. A weak electrolyte breaks apart very little and conducts electricity, therefore, very little. Non-electrolytes, since they don't make any ions, they break up into no pieces, they don't dissociate, they don't conduct electricity. Yet again, I'm going to post a YouTube video on the Canvas page for this, and I'll just call it like the electrolyte video, that will show you someone in their classroom demonstrating how a light bulb works when it's in a strong and a weak electrolyte, and then when it's in a non-electrolyte. And you'll be able to see the amount of electricity that's conducted goes from a lot to none as you work your way down these three different types of solutions right here. Last but not least is a conversation about hydrates. So again, take a moment, pause the video, get this stuff written down. Now, hydrates are things with water attached to them. Not every chemical is a hydrate, but those that are going to have their formulas written with a little dot. It'll look kind of like this. So if I write the formula of copper 2-sulfate pentahydrate, it'll have a dot. So when you see this dot, what it means is that each of these copper 2-sulfates will have 5 water molecules attached to it. So it's almost like you have the copper 2-sulfate, and then you've got one water molecule, and another one, and another one, and another one, and of course another one. That makes 5 water molecules that travel with this one copper 2-sulfate everywhere it goes. Now, every hydrate has a different number of waters, so this number right here could change. It's specific to each individual compound, but that's what it means that it's there, okay? If it's not a hydrate, it's called anhydrous. The benefit of having hydrates is that they change color when they're wet or when they're dry. So they're used lots of times as moisture indicators. The battery in your cell phone is a great example of this, because if you open up your phone and you look at the battery, there'll be a teeny tiny little sticker on it, and I can't remember which color it is when it's dry and which when it's wet, but it's either pink or blue. And you know, if it's wet and you take it to the phone store and you try to tell them that something's wrong with your phone, and they see that there's been moisture on the battery, they'll know that you've gotten your phone wet, and they're going to be able to blame it on you instead of it being like some sort of defect with the phone. So hydrates have a purpose. Here's 3 weird words that go with hydrates. The first one is pronounced efflorescent. You have hygroscopic, and then deliquescent. You can read what it says right here. Oftentimes, these are like the little silica packs that they put in pocketbooks and bags, and it'll say silica gel, do not eat. You know, they use this commonly to keep products from getting moldy or mildewed while they're in storage somewhere. Things that are deliquescent are pretty nifty. I'm going to post one more YouTube video to the Canvas page that will show you sodium hydroxide being deliquescent. It basically is just sitting out in a lid, and you can see the pellets of it, and they start to look like they're almost melting, but they're not. They're absorbing so much water from the air around them that they start to look all shiny. They're basically dissolving themselves is what they're doing. So it's a really short video. You can watch it to get some idea of what deliquescence looks like. Last but not least is writing the formulas and naming hydrates. And then we've got the percent of water in hydrates. So let's look at the formulas and the naming for just a second. A lot of this is old stuff. This half right here that I'm underlining, we should already know how to write formulas for this stuff. It's a throwback to Module 6. This is the ionic naming right here. And then these prefixes are a throwback to Module 7, which was covalent naming. Like, we should already understand all of the underlying pieces. So first and foremost, let's write the formula for iron 3-phosphate. Okay, iron has a charge of +3. Phosphate has a charge of -3. Since it ends in 8, we know that that is a polyatomic ion, so you'll look it up and you'll see that. So therefore, it's going to take one of each. A +3 and a -3 only take one of each to cancel each other out. So here's the formula for iron 3-phosphate. Now, to do the tetrahydrate, what we're going to do is we're going to put a dot, and then tetra means 4, hydrate's referring to water. So we just wrote the formula for iron 3-phosphate tetrahydrate. Now let's do calcium sulfate. Calcium has a charge of +2. The 8 on sulfate tells me that it's a polyatomic. We look it up, we'll see it's SO4 with a -2 charge. If those are +2 and -2, that means it will take exactly one of each of those to cancel each other out. So there's our formula for calcium 2-sulfate. We put our dot, because that's what we do with the hydrate, and di means 2. Hydrate is the water part of it. So the formula for calcium sulfate dihydrate is CaSO4.2H2O. Barium and bromide. Barium is a +2. Bromine is a -1. That means it'll take 2 bromines to cancel out the barium. Now we put our dot. Tetra is 4, and hydrate is again H2O. Alright, now what about naming them? Well, it's just the reverse of what we did. We named this part just like we learned how to do back in Module 6. That would be called iron something and then sulfate. Remember that if it has more than 2 capital letters in it, something is a polyatomic ion. So to figure out the something, look at the charges. Sulfate right here has a charge of -2, so whatever the iron is must cancel that out. So that means it must be a +2. Whoops, I didn't mean to go ahead. So we have iron 2-sulfate, and then we have to name this part of it. I don't know what I'm doing here. Iron 2-sulfate, the prefix for 7, somehow I am no longer writing. The prefix for 7 is hepta. Well, my goodness, y'all. So we're going to write hepta. Let's see what happens now that I've got my color back. There we go. Hepta. And then we're going to put the word hydrate for the water. Now, if I actually wanted it to do that again, I don't know what I just did. So, you know how that works. What about this one? This is tin. Well, remember with tin was an exception that had to have the Roman numeral. This is called chloride. So tin something chloride. Chlorine has a -1 charge, but there's 4 of those. But only one tin. That means the tin has to be a 4 to cancel that out. So tin 4 chloride. This is 5. Well, here we go again. I'm back at this. So let's put, I think maybe I'm hitting a button. And somehow now I've managed to just destroy everything. Okay, let's see if I'm back in business here again. I keep having issues today. So for the 5, we're going to put penta. And then for the H2O, we would just simply put hydrate. Okay, last thing. How do we do the percent water in a hydrate? We are actually going to have several percent problems from this point forward. Anytime we do a percent, remember that to do a percent, it's always a part over the whole. And then we're going to multiply it times 100. So if we're doing the percent water, what we're going to do is we're going to put the amount of water, like the grams of water, over the grams of all, like the whole thing. We're going to multiply that times 100. So with this first one, the percent water, well, water has a mass of 18 grams. This is just like what we did back in Module 9, back when we did the molar mass. We just simply need to find the molar mass of water. So that's going to be 18. But there are 7 of those. So we need to multiply that by 7 on top to find the mass of water. Well, on the bottom, we need to add the mass of everything. So if you add up the mass of 1 iron, 1 sulfur, 4 oxygens, and 7 waters, you should get 278.0 grams. And then we're going to multiply this by 100. So what you could do is make sure that you understand where I'm getting the 18, where I'm getting the 278. Are you able to get these numbers yourself? Then you should end up with 45.32 ... It goes on and on forever. So what do we do with sig figs? Well, my request here of you is that you do 1 decimal place. You had no numbers given to you. Absolutely every single bit of this is coming off the reference table, which means technically it all has an infinite number of sig figs. So we're going to give it 1 decimal place. So our final answer is going to be 45.3%. Now, why do you need to pay attention to that? Because, well, on the quiz questions, if you're not rounding it to 1 decimal place, then you're going to miss it. Same thing goes with pulling the numbers off of the periodic table. I've asked you before to round them to 1 decimal place. If you don't, we're going to come up with slightly different answers. Now let's look at this one. If we do the percent water in this one, I need to do 5 waters this time. It would be 18 times 5 because there's only 5 waters for every 10,4 chloride. Okay, so what about the mass on the bottom of it? Well, on the bottom of it, we need to do the mass of 110, 4 chlorines, and 5 waters. So together, that would equal 350.7. And then we need to multiply that by 100. Okay, if you do this, you should get 25.66, and then the numbers go on forever. So if we do what I said before and round it to a decimal place, that would be 25.7% water in this particular compound. Now, on your practice sheet, you have a lot of those writing, naming of the formulas, and finding the percent water. So you can practice all of that. What I didn't give you is a lot of practice problems with any other kinds of concepts because, honestly, it's mostly definitions. So go do your practice time, and if you need me to help you, let me know during office hours.